Hello, welcome to the class, dear students and my dear friends. So, in the last class, I discussed about the harmonic oscillator, that is isotropic harmonic oscillator in 1D, 2D, 3D cases. That means when the frequencies are same in all directions, and the degeneracy and what type of degeneracy and the energy eigenvalue and the wave function. And here I will discuss today the when the frequencies are not same in all direction, that type of harmonic oscillators are called anisotropic harmonic oscillator. So whenever you say that anisotropic and isotropic gate, at least you have to take 2D or 3D cases, because in 1D you cannot compare the frequency. So for comparison of frequency, at least two frequencies we need, or three frequencies. Okay, so I will say that 2D anisotropic harmonic oscillator. Clear? 2D anisotropic harmonic oscillator. See, let us take an example here. So if suppose your Vxy, the potential is given, suppose half of m omega square, your x square plus 4y square is given, and the range of potential is suppose minus infinity less than xy less than plus infinity. So this is an harmonic oscillator in 2D cases. So if I further multiply it, m omega square x square, or I can say half of m omega square 4y square. Clear? 4y square. So or further I can say m omega square x square, or half of m, here I will write y square. So 4 omega squares are remain. 4 omega square I can write 2 omega whole square. Clear? So 2 omega whole square. So you see, so this is nothing but Vx and this is nothing but Vy. So but in Vx and Vx, the potential in that those both the potentials are not same. Although the displacements are same, but here the frequency is omega, but here the frequency is 2 omega. So the frequencies are different. So it is an anisotropic harmonic oscillator. Now instantly I can write nx and ny, that means energy. So that will be the E nx plus E ny. Clear? What will be the value of E nx? E nx will be nx plus half of h cut, what is the frequency, that is omega, and plus E ny means ny plus half h cut, what is the frequency here, 2 omega. Clear? Or further I can write nx plus, so if I multiply it, it will be 2 ny, and from here it will be half, and multiply by 2 it will be 1. So half plus 1 is 3 upon 2. So h cut omega. So calculation. So this is the simplest calculation. Or I can write n plus 2, n plus 3 upon 2 h cut omega, where n is equal to what, nx plus 2 ny. Clear? This is an important relation. Now this is our nth energy eigenvalue. So what will be the ground state energy eigenvalue, and what will be the first excited state energy eigenvalue, that we have to find out, and the corresponding wave function. Earlier when it was just isotropic, then we directly took that n 0 0, that means nx and y 0, and then 0 1 1 0 combination was the first excitation. Now how to recognize an energy level is first excited or second excited, that is depend on the energy level. The lowest energy level of a simple harmonic oscillator is called your ground state energy level. So clear? So the lowest energy is for, so here if I write n equal to nx plus 2 ny, this is the simplest way. So all values n, nx, ny, so here all the values n, nx and ny, and that will start from 0, 1, 2, 3 dot dot dot. Now which energy will be the ground state? So for ground state, when I will get the minimum energy, if I take n equal to 0, so if I take n equal to 0, then I will get minimum energy. Clear? So then when n will be 0, both nx and ny equal to 0. Clear? That means corresponding to this, I will get energy eigenvalue E00, and that is equal to 3 upon 2 a squared omega. So or further I can write 1.5 a squared omega. Clear? Now then what will be the first excited state? Always remember that first excited state energy is just greater than the ground state, and second excited state energy is just greater than the first excited state, and so on. Clear? Now when n equal to 1, I will get first excited state energy. Clear? Now suppose here if I put 0 here, 0 plus, this is a constant, 0 plus some constant, whatever may be the value, 1.5. if I say here 1, this value will be increased. If I say it is 2, this value further increased. This value, if I say 3, this value further increased. So I will put here that when n equal to 1, that is first excited state energy. Now I have to see the what are the combinations of possible when n equal to 1. So when n equal to 1, then I can say nx equal to 1 or plus ny equal to 0. Any other combination possible here? No. To get n equal to 1, this is the only combination. So it will be E10, and this value will be your 5 upon 2 a squared omega, or further I can say 2.5 a squared omega. Clear? Now so when n equal to 2, that means second excited state energy, what will be the combination? So what will be the combination? And see, when if I take n y equal to suppose 0 and plus n x equal to 2, this is one possible combination. When I take suppose n y equal to 1 and plus n x equal to 0, this is another combination. Clear? So any other combination possible here? No other combination, because to get to satisfy all these values, this is the possible, these two are the possible combination. So for this, so I'll say E20 is your E20 that will be your 7 upon 2 a squared omega, or 3.5 a squared omega, or E01 is equal to 7 upon 2 a squared omega, or 3.5 a squared omega. Now you are getting a difference from the earlier 2D isotropic harmonic oscillator. In that case we got E01 and E10 is the first excited, but here you see the first excited second excited state energy, E01 is also the second excited state energy. Similarly, if I take n equal to 3, third excited state, so how many combinations will be there? First you start from ny value, okay, then it will be very easy, because this coefficient is here, ny equal to 0, I can write here 3 nx equal to 3, this is one combination. Or I can say that n equal to, suppose this is 1, so and again suppose this is 1, this is another combination. This 2 into 1, so 2 plus 1, I will get 3, or 3 plus 0. Any other combination possible here? If I take n equal to 2, so ny equal to 2, so it will be greater. So this is the two possible combination. E30 will be your 9 upon 2 a squared omega, or 4.5 a squared omega, and for this combination E11 is 9 upon 2 a squared omega, or that is equal to 4.5 a squared omega. Clear? Now you are getting the difference, that this is your ground state energy, this will be your ground state, this will be your first excited state, this will be your second excited state, this yes, this will be your second excited state, and this will be your third excited state, this is also third excited state. Now you see, ground state energy, only one energy eigenvalue, so corresponding to one energy eigenvalue we will get one wave functions, clear. So the degeneracy for ground state is 1. Now what will be the first excited state? First excited, you are getting only one combination, so corresponding this combination I will get only one wave function. The first excited state is also the degeneracy of the first excited state is also 1. What about the second excited state? Second excited state we are getting the similar energy eigenvalue, clear, but the combinations are different, these two combinations are different, so corresponding to this wave function, this combination, and corresponding to this combination I will get different wave function. How to find out the wave function I mentioned in the earlier class, so please एक बार आप देख लीजिएगा. So but the wave functions are different but energy eigenvalues are so same, so degeneracy here is 2. So for third excited state, the energy eigenvalues, these energy eigenvalues are same, but corresponding to this combination and corresponding to this combination will get different wave functions. So degeneracy for third excited state is 2. So for first excited state, so I say first excited state your degeneracy is 1, and second yes, and before first excited state ground state the degeneracy is 1. First excited state I got 1. For second excited state the degeneracy is 2, and for third excited state is equal to degeneracy is 3. So this is the way to find out the degeneracy and the different energy level of an isotropic 2D harmonic oscillator. So in earlier case we got when isotropic directly we could write n plus 1 is the degeneracy, but here you cannot write the n plus 1 because it is that n plus 1 degeneracy is holds good for only isotropic case. So to find out the degeneracy you have to proceed in this way. This is the simplest way to find out the degeneracy and the energy level of energy eigenvalue of various energy level. So this is one example for 2D. I hope you got the idea. Now we'll move to the 3D, one example from 3D anisotropic harmonic oscillator. So in 3D case the potential suppose Vx, Y and Z, and that is equal to suppose half m omega square. It can be written as suppose x square, any different eigenvalue. Suppose it is suppose 2 your 4y square plus 9z square I am writing. For the limit is suppose minus infinity less than x, y, z less than plus infinity, clear. So if I say m omega square, this will be the x square, and half of m omega squared m 2, here I can say that 2 omega whole square y square, and plus half of m this will be I can write 3 omega whole square and z square, clear. So this is Vx plus Vy and plus Vz. So the energy eigenvalue E nx, ny and z equal to, for Vx equal to nx plus half h cut omega is the frequency. For Vy and y plus half h cut, what is the frequency, that is 2 omega, and for Vz and z plus half h cut, what is the frequency, that is 3 omega, clear. Or further if I simplify it, nx plus from here 2 ny plus from here 3 z and plus half from here 1 half will come, then 1 plus 1 will come from here, 1 3 by 2 will come, and that is h cut omega. So if I further simplify it, n I can write n plus, so half plus 1 it is 3 by 2, and 3 by 2 plus your 3 by 2 and 3 by 2, that will be your 3. That means n plus 3, that will be the h cut omega, where you will get n equal to nx plus 2ny plus 3nz. So this is the important relation we have got here. All values n, nx, ny, nz will start from 0, 1, 2, 3 dot dot dot. Now 3 is a constant quantity. So if I say ground state, so if I make the table here, n equal to n x plus 2ny plus 3nz, so when n equal to 0, all values must be 0. That means corresponding to this, I will get E0 0 0, that will be 3 h cut omega. Clear? Now when n equal to 1, how many combinations are there? So we have to find out the different combinations. So what will be the combinations? I will get only one combinations if I put nx equal to 1, ny and nz equal to 0, then it will be your, that means E1 0 0, that is equal to 4 h cut omega. And when n equal to 2, so when I will get n equal to 2, so this will be the 0, and this will be, I can say, 1, and this will be your 0, and that is equal to E 0 1 0, and sorry, so yes, E 0 1 0, and that will be your 5 h cut omega. Can I write any other combinations here? So if I write any other, if I put nx equal to, no, I cannot write any other combinations here. But when n equal to 3, so you see, I can say that when n equal to 3, that n, this value I'll put nz equal to 0 here, and this 2 I can write 1 plus 1, then also I'll get 3, then also I'll get 3. And another combinations I can write, suppose if I take nz equal to 1, and these two values are 0, clear? Can I write any other combinations here? Nx, and no, I cannot write. So from this, for this, that means E110, and this is 6 h cut omega, and E001, this is 6 h cut omega. Now you can easily recognize this is what ground state energy, this is your first excited state energy, this is your second excited state energy, this is your third excited state energy, and this is your third excited state energy. Now what will be the degeneracy? Corresponding to ground state energy, I will get only one combinations, so the degeneracy is 1. Corresponding to the first excited, I will get only one combinations. For only one combination, I will get only one wave functions, so the degeneracy is 1, or singly degenerate. Corresponding to this second excited state, again I am getting only one combinations, so your degeneracy is 1. And corresponding to this third excited state, I am getting two combinations, but for these two combinations the wave functions are similar, but their energy eigenvalues are same, so the degeneracy for this level is 2. So in this way we can find out, or further you can write down the wave functions also. No need to write down the wave functions. If it is in your semester exam, then you can write. Otherwise, for competitive examination, or if in your option the wave functions are given, you can write down. Clear? Now how to write, I mentioned in the earlier video. Or basically the degeneracy or energy eigenvalue I can find out in this way. So whatever may be the frequencies given here, so corresponding to those frequencies, that means anisotropic harmonic oscillator, one can find out the various energy levels and the energy eigenvalues corresponding to the various energy levels, and the degeneracy corresponding to the various energy levels. So this is the simplest method to find any, whether it is isotropic or anisotropic case. So I hope you got a simplest idea here. If you think that this is a very helpful, so please share my YouTube channel and subscribe. Please do subscribe. So in the next video I will say when the limit is different, this potential limit is different, then what will happen, then what will be the change in the energy eigenvalue and the wave function. So thank you all of you.